Muted.
Recording? It says the session is being recorded.
Okay, so now it's
Muted.
For those that don't know me, I'm Jeff Boland. I'm the Senior Vice President of the Dragun Corporation. And our webinar today is going to discuss the use of advanced identification methods when evaluating nitrates in groundwater. And as I think we're all aware, nitrates and nutrients in general have been in the news quite a bit lately, and they're becoming the foothold for activism against agriculture, albeit in interrupting agricultural developments, farm expansions, permits, and even litigation. And rightly or wrongly, agriculture is often the first group that is kind of in the crosshairs when a nutrient issue arises. And we're hoping that this seminar gives you guys some food for thought when and if you find yourself in those crosshairs. And as well, the seminar hopefully gives a hint that there may be a way to fight back scientifically. I guess I take it as kind of an honor to introduce Dr. Michael Sklash, who will present this today. Mike is our senior hydrogeologist and our expert in evaluating contaminant fate and transport in groundwater. I've had the pleasure of working with Mike for about the last 27 years. And prior to joining Dragun, Mike was a professor at the University of Windsor. He continued as an adjunct professor at Lawrence Tech University here in the Detroit area. Relative to the topic today, and kind of a side note, one of the advanced methods that Mike will be focusing on today is the use of chemical isotopes to fingerprint and differentiate chemicals, as well as determine the age of groundwater. I should note that Dr. Sklash pioneered some of this work early in his career during his master's and PhD work back in the days of, I guess, dare I say, the dinosaurs. With that, I'll let Dr. Sklash move into the presentation. Thank you, everybody, for coming. We will, at the end of the seminar, unmute everybody and feel free to ask questions at the end of the seminar. Mike?
Thanks, Jeff. Jeff said it was kind of an honor. I'm not sure exactly what that meant. But I'm going to talk about methods to evaluate sources of nitrate. And I'm going to go through things fairly quickly. However, you can see by the number of slides that I have for each topic that I think groundwater is important. And I understand that some of the people who are listening know more about groundwater than others, but I'm assuming, excuse me, a very limited understanding, and then we're going to try to bring you up to a level that you have some decent understanding of groundwater. And whichever technique you use for evaluating sources of nitrate in groundwater, you have to be consistent with what you know about the groundwater. So it comes back to groundwater in the end. I'm not going to spend very much time on nitrate itself or conventional methods, then talk about some of the more advanced methods that you can use. So why is it important to understand groundwater before we think about understanding nitrate sources? These are three of my thoughts. Many lay people have the wrong concept of groundwater in the subsurface and what controls groundwater movement. And I'm going to try to give you what the real picture is. The second point is the subsurface is typically more complex than many groundwater professionals think. When you're trained in university, you get very simple examples of groundwater flow. And then thirdly, many groundwater professionals don't understand the significance of groundwater data from different sources. And what I mean by that is that when you interpret the groundwater velocity, for example, it says something about the geology. And when you interpret concentration differences between point A and point B, that means something about what's happening in the subsurface. So it's kind of interrelationship between the different types of data. Now I use this diagram with the fracture that's up here, just right in here. It's a good indicator of why it's important to really understand the geology. You could drill 100 holes in this area and miss the one fracture that's carrying groundwater. So your concept of how groundwater moves would be incorrect. So it's very important to understand the groundwater situation. So just the basics of groundwater. Groundwater is any water that's below the ground surface. If I dig a hole like you see in this picture, eventually you'll have water come into the hole. Now it could be 1 foot from the surface, or it could be 200 feet from the surface. But somewhere you're going to run into what we call the saturated zone, where all the empty space is filled with water, and that top of the saturated zone is called the water table. Groundwater originates as precipitation that infiltrates into the ground, and about 1/3 of precipitation in humid, temperate areas like the middle of the continent becomes groundwater. The rest of it either flows on the surface or evaporates and so on. So for example, in Michigan, we get about 36 inches of precipitation every year. So on average, about 12 inches of that would reach the water table and become part of the groundwater. So groundwater flows through spaces between grains in a soil or between grains in a rock. On the left-hand picture, you see a Bic pen cap next to sand, and in this case, the groundwater flowing through the sand would go between each individual grain. Picture on the right is fractured limestone bedrock, and in this case, groundwater would flow through the grains of the rock, but it would also flow between those big empty spaces. So it's a little bit different, but in most cases, we're dealing with the example on the right, groundwater flowing through small openings between grains in the soil. The idea that groundwater moves in veins and rivers is not the norm. You know, rarely do we get groundwater moving to rivers. We might get it in areas where there are caves, but in general, we're speaking about groundwater flow that's through grains of soil. This is a couple of examples of how the geology might affect groundwater movement. So how quickly does groundwater move? Well, on the picture on the left, we've got sand on the left of that and clay soil on the right. These are cores that we've taken. Groundwater flow a lot quicker in the sand than it will in the soil, many thousands of times quicker potentially. On the right, we see cores taken from a different type of drilling technique, and we can see some gravel, some sand, and clay soils. All these soils will transmit groundwater at different rates, and we have to understand how quickly groundwater can flow within a given geologic environment. These are two complications that we've seen that are fairly common. In the Great Lakes area, we get what are called fractured clays, and we can see these wet areas in the base of this pit where we're doing an investigation of whether we can put in a manure pond in this area. And you can see the wet spots indicating fractures. So typically, if you're not looking, you would miss the fractures. Think this is a great spot, but not so great with the fractures. And on the right, we have what's called varved clays. And varved clays occur where there's been a glacial lake, and we get these horizontal laminations that allow groundwater to move quicker than the massive part of the clay. So these would complicate the interpretation of how quickly you'd expect groundwater to flow. But in general, how quickly does groundwater flow? I use some calculations for example sites, and every site is going to be different. If we have sandy soil and the ground is fairly flat, the groundwater is probably going to move somewhere around 4 feet per year, maybe twice that or half that, but that kind of ballpark. If we had the same groundwater flow, not in the same environment, but in a steeper environment, and the material was gravel, you might get flow at about 400 feet per year. And then if you had material like we see at the end of this shovel, groundwater flowing through that would be less than a foot per year and probably less than an inch per year. So there's a wide range of how quickly groundwater can flow, but in general, it's fairly slow. It's not like surface water. It flows fairly slowly. So we've got the groundwater flow rate. How fast do chemicals move? It will depend on the groundwater velocity, but it also depends on the soil. Some soils prefer or tend to attach themselves, or vice versa. The chemical would tend to attach itself to the soil. Something like a clay soil would tend to do that more readily than a sandy soil. In our case, for nitrates, that's not going to happen, but it can happen if you're looking at some other chemicals. What direction does groundwater flow? And in general, we use what's called a groundwater contour map to indicate that. And the groundwater contour map has a number of different components. It's got these contour lines in blue, which are lines that join points of equal groundwater elevation. And they've got different values. So it's like contours on a hill, but this is contours on the water table. The groundwater flow is at 90 degrees to the contours, and the groundwater flow is from the high contours to the low contours for the water table. So in general, groundwater flows at right angles to the contours from high to low. And we use a technique called the three-point method to figure that out. And basically what we're looking at is assuming the water table, the top of the zone of saturation, is a plane that has a slope. And if we know 3 points of elevation, like on this pyramid, 1, 2, 3, then we can interpolate the elevations between those points and come up with a map or a contour map of the elevations. So how do we know all this in the field? We drill holes with rigs, drill rigs. There's an auger rig, a sonic rig, and a geoprobe rig, and these all use different methods to get soil samples so that we can figure out how quickly groundwater is going to flow, and to put in wells so that we could get water levels and to sample the groundwater. And we look at the soil. We have a geologist look at the soil. Or in this case on the right, we've got what's called a hydraulic profile rig with a geoprobe, which allows us to identify permeable zones in real time by injecting water into the formation and seeing how much pressure is required. And then once we have a hole in the ground, we could put a well in. And well is just a pipe. It could be PVC or stainless. The bottom part of it has what we call a well screen, which is generally got openings. This is a demonstration screen just for show with wide openings for gravel, small openings for sand. This one at the bottom is 1/100th of an inch, and that's typically what we would use in environmental investigations. And then we measure water levels using what we call an electric contact gauge, which is a probe which goes into the well, and it will set off a buzzer or a light when you reach the water table, and we measure the depth to the water table. So that in a nutshell is Groundwater 101. This slide here is Nitrate 101. Nitrate is chemical formula of NO3. That means there's one nitrogen atom, which we see the blue one, and 3 oxygen atoms attached to it. Nitrate can originate naturally in precipitation or from rocks. It can come from chemical fertilizers, come from manure, from animals, from septic fields, from landfills, and other sources. Nitrate can form from and into other forms of nitrogen. So we're looking at the form of nitrogen which we commonly find in groundwater. The regulatory limit for nitrate is generally 10 milligrams per liter, which is 10 parts per million. And nitrate travels at groundwater velocity. It's not held up by the soil at all. So if we know the groundwater flows at 4 feet per year, nitrate will move at 4 feet per year. So how do we look at identifying nitrate sources in groundwater? This is a typical example, and I like using this one because it's a small dairy herd near my daughter's cottage on a small lake that you can see is having some issues. But basically what we need to do is figure out what's the upgradient side. This blue arrow is indicating the direction from which groundwater flows. Yellow arrow indicates the direction groundwater leaves the little dairy. And what you need to do is know the nitrate concentration going in, nitrate concentration going out, which you would get from sampling groundwater in wells on the upgradient and downgradient side. And then you do a balance. What's the difference? Is there more nitrate going out from the dairy or coming in from the dairy? If it's more coming out, that means that the source of the additional nitrate is the dairy. That's the traditional, conventional, simple method of identifying a source. But what if the nitrate coming in is elevated? It can be from other animals, like donkeys. Rare, but could be. Canada geese are culprits sometimes. It could be from septic systems, or it could be from chemical fertilizers. So how can we tell what's going on in a complicated situation? So I'm going to talk a little bit about some advanced identification of nitrate sources. So the first one relates to the concept of knowing what's up gradient and what's down gradient at a site. And this graph that you see is what we call a hydrograph, a groundwater hydrograph, and there's time on the x-axis and water level on the y-axis. And we have 3 wells shown here, well A, B, and C is the gray one. And we would do our simple triangulation within these wells to determine what's upgraded and downgraded. But what you see in this case is that it's not always the same. If I look at this spot here, MWB, monitoring well B, has the highest water level. Groundwater would come from that direction. But over here we see monitoring well A has these spikes in groundwater elevation due to, in this case, ponding, but it could be seasonal ponding, rainfall, episodic ponding, could be a dam controlling groundwater, could be leaking pipes, could be pumping causing changes in water level. But for whatever reason it is, we see sometimes A, sometimes B, sometimes C are the highest water levels. That means that the groundwater flow direction is changing. And we can use what's called a data logger, which is a device that we can put into the well, and it will basically weigh the water column on top of it and give you continuous readings for months if you want, at periods like 15 minutes or so that you can get a continuous record. You could see which way the groundwater is flowing for long periods of time. This is another site where we're looking at, was there a change in the upgradient direction? And this, basically, we did three-point methods to determine groundwater flow direction, which are these arrows. And you can see the arrows go in different directions depending on the season. Each one is a different month. And the red bar, the relative length of that, shows that the nitrate is changing depending on which way the groundwater is flowing. So it's important to note, if you're doing the in and out balance of nitrate, to make sure that groundwater flow direction doesn't change much during the season, or if it does, then you need to know the implications of that. In most cases, groundwater flow directions will change, maybe 15 degrees or so annually, but in certain cases where you have these other factors involved, it could change a lot. The next little bit that I'm going to talk about has to do with evaluating the age of groundwater. And I'm going to call this legacy nitrate. So what we have found during the past 40 or 50 years of doing isotopic investigations, and I'll explain what that is in a minute, we've actually looked at water molecules in storm runoff and in snowmelt runoff in streams. And what we found is that a lot of the water that happens during a storm event, which in your mind you might think is coming from the rainfall, it's actually coming from the groundwater. So the groundwater will have a lot more control of the nitrate concentration than you would think in a storm runoff event. And this kind of surprised people in the 70s and 80s, and it's becoming more and more accepted now that groundwater or old water or legacy water as an important contributor to storm and snowmelt runoff in streams. So it's not so much what you do now on an agricultural site to control nitrate, and that's important, but it's also important is what has been done in the past, and also what's the relative contributions. So what's an isotope? An isotope is just a type of an atom. So for example, in water, H2O, the hydrogen H and the O oxygen has different types of different versions basically, and that type of version will have different physical properties. So in water, for example, there's 3 different kinds of hydrogen, H1, H2, and H3. They have different masses. They weigh different amounts. They behave chemically the same. They look the same, but they behave differently. And the same thing with oxygen. There's 3 types of oxygen, O16, O17, and O18. We're going to talk about the ratios of the heavy H2 and O18 to their lighter counterpart. Tritium's a special case Tritium is radiogenic, meaning kind of radioactive, and it can also be used in manure, but I'm not going to talk about that today. So this is an example where you can use isotopes in water to determine how old the water is that you're looking at. So what we see here is a graph showing time, 1960 to 1980, versus oxygen-18 concentration. And so we've got about 15 to 20 years of record here, and you can see that there's variation in the concentration in precipitation. And what we see is in the cold months, there's more negative values. In the warm months, there's less negative values. So different concentrations of oxygen-18 and also H2, deuterium. And if we summarize that, so this is that Midway Airport, and sorry, we see from the various months in the winter months, 12 and 1 and so on, we've got these very negative values. And in the summer months, we have less negative values. This happens at every location where you'll see a seasonal variation. This is a map showing the average annual oxygen-18 in precipitation in the northern hemisphere. And you can see Detroit there. Detroit, the average rainfall will be somewhere between -8 and -10. And this map is after Joel Gatt, 1980, and I spent some time working with Joel, actually not too far after this on my first sabbatical. Groundwater will take on a similar value, not exactly the same, because some of the precipitation runs off, some of it evaporates, but generally you can use this map to estimate what the groundwater will be like in every spot. So now that we have the groundwater or the old water, what's the precipitation look like? So if we can do a simple two-component mixing, meaning we've got the old water in the ground, which is the groundwater, we know that concentration, and we measure what's going in by sampling the rainfall. You know, we would stand out with big funnels and collect rainfall water. And then if we measured the water in a stream, we could figure out how much old water and how much new water was in that mixture. So the first 10 years of my career, I would stand out next to a stream in the rain and sample water from the stream and figure out what that mixture meant in terms of what was there before and what was there because of this storm event. So if the mixture value was -10, then that would mean all of it came from here. If the mixture value was -12.5, means that it was 50% stored water, 50% event water. The same thing goes with the nitrate. That would mean that half of the water came from old water, legacy water, and half came from the new rainfall. So this was pretty significant to the understanding of where rainfall or where stream water came in storm events. And we did also work, and other people did work during snowmelt events, and it was similar. Again, it's not just the snowmelt and the surface runoff from a site that affects the nitrate concentrations in surface water. Here's another method or another application of that. This is a site that we looked at where we were looking at the groundwater concentrations of nitrate on the upgradient side. This is what the old water looked like, the groundwater, somewhere around -10. The one well that was problematic was a little bit different, -8. But we had a big storm event, and we were able to sample the ponded water that was right next to that well that was -8. We can see a close-up of it here. And the well changed from being that concentration of isotopes to that concentration within that storm event. So what that meant was that you couldn't use that well to give you an idea of what the groundwater nitrate was because it was rainwater. So it's important to note that your water that you're dealing as representative of groundwater is actually groundwater and not a mixture. This is a study that was done by the U.S. Geological Survey in Delaware that looked at residence time and nitrate concentrations in the Delmarva Peninsula on the East Coast. And just the one sentence is important because it says, the estimated aggregate residence time of groundwater contributing to surface water for the entire Bucks Branch watershed in the most downstream samples approximately 19 years. So that means that if you go to the stream, and you look at the nitrate concentration of the stream, it's not only representing what you did in the last year or the last 5 years, it's representing what went on decades before. And this is the same for just about any watershed, that what you're seeing is a combination of old and new water. Quickly, we're going to look at nitrogen isotopes and oxygen isotopes in the nitrate itself. So now scientists can take apart the nitrate in a groundwater sample and look at where it came from. So we're going to take a look at what that means. So this is my interpretation of where, if you analyze a groundwater sample for nitrogen 15 and oxygen 18, these would be the categorizations or the boxes where you could characterize the source of the water. So this blue box here, anything that falls in that is animal manure. The dashed line box is wastewater. I'm colorblind, so I can't remember what color this is chemical fertilizer. Precipitation is up here. So the important demarcation line is the one between animal manure and fertilizer, in this case chemical fertilizer. And based on a number of articles that I've read in the literature recently, the demarcation should be similar to what I've showed it. But that's not always accepted by, say, the EPA, for example. And I'll show you a couple examples. So this is a USGS study in Nebraska where they were looking at nitrogen 15. They found a range of +2 to +6. And what they concluded was these samples down here, which turned out to be the more recent groundwater, were indicative of chemical fertilizers. And so that is significant because without the isotopes, they wouldn't have been able to distinguish between those. This is the Hack Dairy data from the Yakima Valley. Just one that is pretty much definitive. There's 12.8 milligrams per liter nitrate in this spot here. They concluded was animal waste, but they concluded, or their opinion was, 2 was the demarcation line. So anything that was near 2 for nitrogen 15, they said they couldn't distinguish. So this is fertilizer or animal waste. This one they said was indeterminate, and this one they said was fertilizer and or animal waste and some atmospheric. So there's some interpretation that differs between people who use these isotopes for identification. So those methods with the isotopes, the nitrogen isotopes, can distinguish between chemical and manure sources of nitrate, but you may have something more complicated, and I'm not going to go into detail in this, but in the Yakima study, they use things like microbiology, organic compounds, pesticides, veterinary pharmaceuticals, and veterinary hormones to distinguish between chemical fertilizers and nitrogen source or nitrate sources from cattle. Some of the other publications that I've looked at related to septic fields for human identifiers would be caffeine in your coffee, sweeteners in your coffee or tea, codeine or Tylenol. That could be identified in as a source of nitrate. And finally, microbial source tracking is something that I've been looking into lately. I've been talking with Joan Rose from Michigan State, who's done a fair bit of this. Microbial source tracking allows you to differentiate between different types of animals. And the work that they've been doing is in watersheds, more on the end of the watershed to see, as a large scale what the watershed is producing in terms of different types of sources of nitrate from animals. So kind of we've gone over a lot, just want to summarize in a few statements. Understanding groundwater is critical to determine the sources of nitrate. So no matter what advanced technique you use, it has to be consistent with the groundwater flow direction, the groundwater velocity, and so on. The simple up-gradient, down-gradient nitrate comparison is sometimes useful in simple situations. Advanced techniques are useful for evaluating nitrate sources if the scenario is not simple. Could be different changes or changes in the groundwater flow direction. Could be multiple potential sources. And then just based on experience, not just with nitrogen 15 isotopes, but any type of advanced technique that you could expect challenges from the regulators, especially if it doesn't fit their conceptual model of where nitrate sources are.